one of the most important property when we're talking about function is whether that function is continuous or discontinuous. So what does it mean by saying a function is continuous? Let C be a real number that is either an interior point or an endpoint on an interval in the domain of f. The function f is continuous at C if the limit exits at C and the value of the function at C is the same as the limit. Okay, the function is right continuous at C or continuous from the right if the limit at x approaches C from the right of f of x equal to f of C. The function is called left continuous at C or continuous from the left if the limit at x approaches C from the left of f of x is equal to the value f of C. We have a test for continuous function, and if a function is continuous, it has to meet the three following conditions. The value of f of C exit, the limit at x approaches C of f of x exit, and these two values, the limit at x approaches C of f of x is the same as the value of the function at C. Now determine where each of these following function is discontinuous. So let's take a look at the first function. Well, this is a classic function that we see all the time, right? So we know that this function here this function here is undefined when x is equal to. Okay. So I can say that, well, that's the case. This means f of 2 does not exist. So then f of x is discontinuous at x equal to, and it's failed the first condition. If f of x equal to 1 over x squared for x is not 0, and equal 1 if x equal to 0. Okay, so let's go through our all three conditions. At x equal to 0, f of 0 is equal to 1. Let's see what happens when the limit at x approaches 0 from the right. Then we look at the of f of x. We are looking at the limit at x approaches 0 from the right of 1 over x squared. Well, here we divide it by a really small number, right? At x approaches 0 from the right, we square that number, we get that number even smaller. So at x approaches 0 from the right, the limit is positive infinity. The limit at x approaches 0 from the left of f of x is equal to the limit at x approaches 0 from the left of 1 over x squared. Again, this equal infinity. This then saying that the limit at x approaches 0 of f of x is equal to infinity. Now this is not the same as the value of the function at 1. So therefore, f of x is discontinuous at x equals 0. Let's take a look at part C. Let's see what happened at 2. We know the function f of x. F of x is equal to 1 at x equal 2. So f of 2 equal 1. What happened to the limit at x approaches 2 from the left of x squared minus x minus 2 divided by x minus 2. We will factor the numerator and simplify. So we look in the limit at x approaches 2 from the left of x minus 2 times x plus 1 divided by x minus 2. This is equal to the limit at x approaches 2 to the left of x plus 1, and this equal to 3. Okay, so right off the bat we can see that this is not the same as f of 2. So then f of x is also discontinuous at 2. The greatest integer function is defined by x equal to the largest integer that is less than or equal to x. So for example, 4.34 is equal to 4. Negative a half is equal to 1. Okay. This means this function, if you draw this out, 1, 2, 3. So 1, anything that is a little more than 1, that make 2. That make 2. Okay. And anything that a little more than 2, that make 3. And 2 equal 2. 3 equal 3. So then you can see there is a jump. There's a jump. Okay. So then f of x is discontinuous on its domain. This is just jump. So here's the function. If you actually grab it, that's what it looks like. And here you can see, in the first case, we have a hole here that is a discontinuous, and we have a hole. Okay. Here we have an infinite. There's a distance between the value of f of x and the limit. So here we have a jump. Same here, we have a jump. We want to find the value of a and b that make the function is continuous everywhere. Again, the function is continuous everywhere if f of c equal to the limit at x approaches c of f of x. So there are 2 points in question, the 2 values in question, that is 2 and 3. Okay. So at x equal 2, let's take a look at the first part. The function will exist if the limit at x approaches 2 of f of x is equal to f of 2. Okay. First, let's consider what is the limit at x approaches 2 from the left. At x approaches 2 from the left, f of x, let's look at our number line. We'll divide this out. Here's 2 and 3. So this part here is for this portion. It belongs here. And this is here. So at x approaches 2 to the left, the function becomes x squared minus 4 divided by x minus 2. We want this equal to the limit at x approaches 2 from the right. At x approaches 2 from the right, we'll consider ax squared minus bx plus 3. Okay. As x approaches 2 from the left, we have the limit at x approaches 2 to the left equal to x minus 2 times x plus 2 divided by x minus 2. This equal to 4. This means we want the limit at x approaches 2 from the right of ax squared plus bx plus 3 equal to 4. So then, a times 2 to the second plus b times 2 plus 3 have to equal 4. So 4a squared plus 2b equal 1. We'll leave this here for a moment. Now let's take a look at what happened at 3. At x equal 3, we want the limit at x approaches 3 from the right of f of x is equal to the limit at x approaches 3 to the left of f of x. At x approaches 3 to the right, we have the limit at x approaches 3 to the right of 2x minus a plus b, and we want that equal to the limit at x approaches 3 to the right, to the left. That is ax squared minus bx plus 3. This here need to be a negative. Let's fix that. Now because we have both polynomial function, this I can plug it in. 6 minus a plus b then have to equal to 9a minus 3b plus 3. So then 10a minus 4b have to equal 3. And this will say 4a, right? 4a minus 2b. Now that I have two equations with two unknowns, I can solve this equation for a and b. Okay. 4a minus 2b equal 1. So then 2b equal to 4a minus 1. I will substitute that into the second equation. So 10a minus 2 times 4a minus 1 equal 3. 10a minus a8 plus 2 equal 3. 2a equal 1. A equal half. A equal half. 2b equal 4 times a half minus 1. 2b equal to 2 minus 1. b equal 1 and a half. Okay. So the a and here's b. So let's double check with our function to make sure that we get what we want. What happened when x equal 2? So here, f of x equal to x squared minus 4 divided by x minus 2 if x is less than 2. Ax squared minus bx plus 3 if 2 is less than or equal x less than 3. 2x minus a plus 3 if x is greater than or equal 3. You can double check the value of f of x at x equal 2 and f of x at x equal 3 with the value of a and b to see whether we get the same value as the limit. Okay. And you can do that on your own. Here we get some theorem. If f and g are continuous functions, at x equals c. Again, this is we have this similar with the limit function, right? And we have the operation of a function as well. If the function is continuous at c for both f and g, and is not being 0 at g of c, then all our operation still work, and this function, the resultant function, are all continuous function. If f is continuous at c and g is continuous at f of c, then the composition function f composed g is also continuous at g. And here's the most important theorem of all. Any polynomial is continuous everywhere. That is continuous on its entire domain, is from negative infinity to infinity. Any rational function is continuous whenever it is defined. That is continuous on its domain. So let's take a look. Why does this function is continuous as every number in its domain and stated domain? Well, we know that f of x is equal to sine of x divided by x minus 1. So then we go ahead and let g of x equal to sine of x. This continuous on its domain, like continuous. On negative infinity to infinity. E of x equal x plus 1. This also continuous from here. However, sine of x divided by x plus 1. This define when x is not negative 1. Okay. So this function is continuous in its domain. And that is for all x such that x is not 1. Now, for the next one, well, x squared is continuous from negative infinity to infinity. Square root of 2x minus 1 is defined when 2x minus 1 is greater than or equal to 0. So x is greater than or equal to half. This means f of x is defined on the interval x such that x is greater than a half and continuous in its domain. If the limit at x approaches c of f of x equals b and g is continuous at the point b, then the limit of the composition function is given as follows. Let's see, we can use that to do some computation. The limit at x approaches 0, the tangent of pi over 4 times cosine of sine of x to the 1/3. So what it's saying is we can bring the limit inside. Okay, so let's go ahead and do that. Equal to tangent the limit at x approaches 0 of pi over 4 times cosine of sine of x to the 1/3. Okay. Now I can bring the pi over 4 out front by the limit law. Then I get tangent the pi over 4 times limit at x approaches 0 of cosine of sine of x to the 1/3. So then tangent of pi over 4. Now, I can't bring this in any further, right? Because it's a cosine of a function. Now, but I can see that here, look, if I put x equal to 0 into this function, sine of 0 equal to 0. So the limit at x approaches 0 of cosine of sine to the sine of x to the 1/3 is equal to cosine of 0. That equals tangent of pi over 4, and that is 1. We will use this continuous function to talk about the intermediate value theorem for continuous function. If f is a continuous function on a closed interval a b, and if y0 is any value between f of a and f of b, then y0 equals f of c for some c in the interval ab. Okay. So it's just saying, well, here you have a function, and if it's continuous, this means in between this, for x equal to c, there have to be a value y0 that make this happen. Okay. And we want to use this to show that there are 0 in between the intervals. So think about this. Say if I have a function that is continuous in the interval from a to b, if f of a is positive and f of b is negative, okay, then my function maybe look like this. Then there would be guarantee a value c in somewhere such that f of c equal to 0. Right? So that I can just show, well, then maybe that should be the case. Show that f of x equal to x minus cosine of x have at least one 0. Okay. So let's choose an interval. Here we can see that f of x is a continuous function. F of x is continuous in a domain of negative infinity to infinity. And let AB be the interval of concern. Okay. So note that f of 0 is equal to 0 minus cosine of 0, that equals negative 1, and that is less than 0. F of pi over 2 is equal to pi over 2 minus cosine of pi over 2, that then equals pi over 2, that is greater than 0. Right? So then, let the closed interval AB be the interval 0 pi over 2. Then clearly, there is a number, there is a value x equals c in the closed interval 0, in the open interval 0 pi over 2, such that f of c is equal to 0. Okay. Given a function f of x is continuous over the interval 0, 2, f of 0 greater than 0 and f of 2 is greater than 0, can we assume that f of x have no 0 in the interval? We cannot assume that's the case because the intermediate value theorem only allows us to conclude that we can find a value between 0 and 2. It doesn't allow us to conclude that we can't find other values. Okay. So for example, let's say if f of x is equal to x minus 1 squared. Well, let's take a look at this graph. This is the graph that shifted 1 to the right. Okay. So here's 0 and here's 2. Clearly, f of 0. So here you can see that f of 0 is equal 1. F of 2 equal 1. They both greater than 0, right? However, f of 1 is equal to 0. So we can't conclude that there is no 0 in the interval. We only can conclude that there exists a 0. That doesn't mean. So if you recall the theorem, in the theorem itself, it's saying that if f is continuous, then any interval on which f change sign contains a 0 of the function, somewhere between the point where a continuous function is positive and the second point where it is negative, the function must equal to 0. It's saying there exists a point that happen when there is the change of sign. It doesn't say that if the sign doesn't change, then you can't have the 0. So make sure that you understand that, distinguish that clearly. Okay. So no, that is not the case.